Okay. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to all students. So let's do some examples to enhance your understanding in the topics of wind loading. So basically the objective in this topic is for you to determine what is the wind pressure. Okay, what is the wind pressure acting on the structure? So basically we have a building, we design the buildings, but we as usual we determine the uniformly distributed load, which is dead load and live load, but at the same time we have to be aware that there are another sources of loading, what we call as a wind pressure. So this wind pressure, we cannot just assume the pressure. There is a way how you calculate based on code. Okay, so for you to do this, you have to make sure that you have the MS, okay, MS wind loads, which is MS1553 2002. Okay, this is the wind load code, Malaysian standard. So let's look at this exercise or examples. So these examples is to determine the base shear and overturning moment for a structure, okay, for a structure which is 4-story at 10 meter, alright, whereby if you can see the plan view is 12 meter width and 8 meter breadth. And here are the details of the structure, where the proposed 4 stories stand at 10 meter, which means the total height is going to be 40 meter, is located at Ipoh city center, where it has been determined that at Ipoh the frequency is 4 Hz. And for these examples, we assume effect of shielding hills ridge are negligible. Okay, before we continue, let me give you some general idea on this wind loading topic, and what I can say is a summary of this topic. So as I said earlier, the objective is for you to determine what is the design wind pressure acting on your structure. So the design wind pressure is given in clause 2.4.1 and from equation 2. So if you can see here, for you to reach or for you to calculate the design wind pressure, you must know all these parameters, where all this parameter is given in these clauses. For instance, C dynamic, the coefficient factor, what we call as a dynamic coefficient factor, is given at section 6. For all building which is more than 1 Hz, it will give you 1, the coefficient factors. And then C fig will give from section 5, and you have V dash, okay, and then you have the 0.5 density of air, which you calculated is going to be 0.613. And then for you're not able to get the design wind pressure if you are not able to calculate all these parameters. So for V dash is the longest part, where you need to find what is the V dash from these equations, and then the factor is taken from table 3.2. The side wind speed is taken from clause 2.2, and to get this, there are a lot more parameters that you need to consider, where it gives in this parameter. So the easiest way for you to determine the design wind pressure is by calculating backward, meaning that you need to calculate this first. To calculate this, you need to find all these parameters. When you get all these parameters, insert it into these equations. Once you get these equations, you include it in this. So this one will be settled. This one is straightforward, 0.613. This one you can get from section 5. Here you can get from section 6. And finally, once you get all these parameters, you get the design wind pressure that you need to calculate. So once you get the design wind pressure, therefore you can find what is your base, shear and overturning moment for the proposed structure. Okay class, before we start, make sure you have with you your MS standard design code. So if you look here, the code, okay, there are many codes available for determined wind loading on structures. For this lecture, the code shall be MS1553 2002, which is code of practice for wind loadings for building structures. Alright, so make sure you have this code with you. Okay, let's now we start to calculate the design wind pressure. So just to recall from our notes, okay, it's given that the design wind pressure is in unit Pascal, okay, in unit Pascal, which is calculated from clause 2.4.1, and it is given that these equations, whereby here is the density of air, which is 1.225 kg per meter cube, and this is the design wind speed, this is the aerodynamic shape factor given in section 5, and then here is the dynamic response factor, which shall be taken as 1 unless the structure is wind sensitive. You have to refer to C section 6. Just bear in mind, when you calculate the design wind pressure, okay, you have to make sure that the minimum wind pressure must not be less than 0.6 kilopascal. That is the key thing. You cannot have below than 0.65 kilopascal. So what happens if you have less than 0.65? So when you have below than 0.65, then you have to use this minimum value. Okay, so from clause 2.4.1, so let's now we find what is this value. As you know, it has been stated here that the density of air is 1.225 kg per meter cube. So here you just calculate first 0.5 times with, which is 1.225 kg per meter cube. Alright, so you need to find what is your V dash. Okay, so V dash is the design wind speed times with design wind speed, and your C fig is the aerodynamic shape factor, and C dim. So now let's first calculate what is your V dash. Okay, so now calculate your design wind speed. Design wind speed, which is the V dash. So design wind speed, recall back to your notes. Okay, it's given that from clause 2.4.1, which is design wind speed is equivalent to design wind speed times with the important factor, which is given in table 3.2. So now let's see what is the V dash and V seat. So now we know that V dash is equal to V seat times I. Okay, so again we need to find what is your V seat. V seat is equivalent to Vs, which is your basic wind speed, times with the MD, which is your wind directions coefficient factor, times with MZ cat, which is what we call as the terrain and height of the structure category, and then you need to multiply with MH and MS, which MH is the local topography hills and MS is the shield and neighboring by buildings. Okay. Okay, for VS, you can determine from either you use figure 3.1, which is this figure, alright? So it's not very clear, this figure, so you have to use this figure. Okay, so this figure 3.1, it is locating, it indicate that which zoned area is your structure. So in our case, our structure is Ipoh. Okay, so this is Ipoh. So when it is located at Ipoh, alright, you have to read at this box. It says that for basic wind speed, okay, so they have a different zones. So you have, if you have zone 1, so VS is 33.5. If you have zone 2, VS is equivalent to 32.5. So in this particular case, your Ipoh area is located at zone 1. Okay, it is located at zone 1. So when it is at zone 1, so therefore the value is 33.5. But if you don't want to look at this figure 3.1, you can refer to your MS Malaysian standard for wind speed, which is MS1553 2002. You can see that your wind speed also can be found in table form as to what you can see here. So now you know that from either figure 3.1 or table 3.1 from the MS clause, you will get your VS is equivalent to 33.5 meter per second. Okay, so then let's look at what is your MD. Okay, determine MD. So MD, okay, MD is given as the wind directions. Okay, MD is your wind directions. So for your wind directions, okay, in these examples, there are no information given. No information on wind direction. Okay, therefore we can assume. Okay, we can assume MD is equals to 1.0. Alright, and let's now refine what is your MH. So MH is what we call as the local topography hill ridge. Okay, where as defined earlier, MH is local topography. And if you remember in the questions, okay, it stated that we assume effect of shielding hills ridge are negligibles. So because of negligibles, so we can take the value of MH equals to 1.0, and shielding also negligibles, so shieldings because we took it as 1.0. So the only remaining parameter that we didn't find yet is the MZ cat. Okay, so MZ cat, okay, to determine MZ cat, which is what we call as the terrain and height of the structure. Okay, so we need to refer to table 4.1 in MS 1553, okay, 2002. So for you to determine this, okay, so for you to find MZ cat, which is from table 4.1, okay, let me show you here. So MZ cat is from clause 4.2. Okay, it is the multiplier for the terrain or height category. So it refers to ground conditions or obstructions within 3 kilometers of the site which the approaching wind must blow before it reaches the structure. So there are 4 categories of terrain. Okay, you can see the first category, which is exposed open terrain with few or no obstructions. So for terrain category 1, let's say the questions given to you, okay, let's say the question given to you says that the building is located in front of the seaside at Pulau Langkawi or Langkawi Island. So in that particular case, therefore you need to take category 1, which is open terrain, no obstructions. And if you look at category 2, okay, category 2, which is open terrain with grassland and few well scattered obstructions, 1.5 meter to 10 meter height, and these can be examples like large paddy fields or areas near mining pond. So because it is open terrains, you can imagine that the building that you're going to build is open space. There are no other buildings which are closely related and no obstructions from 1.5 to 10 meter height. So the best examples can give you if you have a building which you're going to build in the large paddy fields or area near mining pond, or there is no obstacles. Okay, so now let's look at another category. Okay, so another category is category 3. Okay, if you look here, category 3. So category 3, okay, is terrain with numerous closely spaced obstructions. So now you can imagine that the higher the category, it means that there are more obstacles close to your structures. So here is 3 meter to 5 meter height. Example, suburban housing areas surrounded by palm oil estates or rubber estates. Okay, and last category, which is category 4, terrain with numerous large and closely spaced obstructions. So category 4, you have very close obstructions, 10 meter to 30 meter height of buildings, and the best examples for category 4 is Kuala Lumpur city center, where if you can imagine in Kuala Lumpur city center, there are a lot of buildings are closely related. So just to highlight that terrain category can change over the life of the structure. Yeah, it's obvious because it can happen whereby the paddy area is transformed to a suburban or urban area. Okay, so thus suburban housing areas can become downtown as development. Yeah, sure. And the terrain category change from category 3 to category 4. So towards the development, some areas which it's previously is a paddy field, and it can use it for another source of constructions development. So the height, you can see height class 4.2 refer to the distance from the local ground level to the level in which wind speed is to be determined. The higher the level, the higher is the wind speed. If you can see here, alright, examples here. So the wind speed at level 20 of a condominium is higher than that at level 3, because the wind speed, if you see this is the height of your building, the wind speed will be higher, or it will increase gradually from bottom to top. So here you can have like some sort of like that distributions. Okay, so and there is a distributions of wind speed which increases from ground level to the roof level of tall buildings. So the effect of terrain, that the one that we wanted to find now, which is the MZ-CAT. So this is the one that we wanted to find, is the effect of terrain and height is accounted for using the multiplier MZ-CAT, where you can see in clause point 2 and table 4.1 that the table from MZ-CAT increases with height. Also, terrain category 1 is the least favorable, whereas the category 4 is the most favorable. Alright, so now in our examples we can see that we need to find what is the distributions of the structures. So we have those structures, okay, which are okay, 10 meter at 4 stories. Okay, we have 10 meter at 4 stories. So MZ cat, you can draw like a table M, and then the value of MZ cat. Okay, the value of MZ category MZ category. So you can draw this table MZ cat, whereby at each story this is 10 meter, and it is 20 meter, 30 meter, and 40 meter. So you have here 10, 20, 30, and 40. So the MZ cat value you can refer in table 4.1. So this is table 4.1 in MS1553 2002. Okay, so I'm sure you have the soft copy of this table. So from this table you can see which terrain category is your structure is. Alright, so in your structure, your terrain category is, you can say it is category 4, because in Ipoh itself they have a lot of building which is closely into each other, and the height is significant, and because of that we choose the Ipoh under the terrain category 4. So for the height, okay, so here you have this, okay, 10, 20, 30, and 40. So now we look at terrain category 4. Okay, terrain category 4, for a 10 meter height it gives you 0.75. For 20, okay, 20 it gives you 0.75, and if you go for 30 it gives you 0.8, and then if you go for 40 it gives you 0.85. Okay, so if you here, then you just can insert the value, whereby at 10 meter is 0.75, here is 0.75, here is 0.80, here is 0.85. Okay, for the purpose of these examples, okay, we choose the most highest coefficient factor, which is 0.85, but basically you need to calculate for the rest of the story as well, which is going to be the same for the VS, which is the wind speed. And the idea to get this, for you to get this V dash, the idea for you to get the design wind speed is you wanted to look at the profile of your structure. So you wanted to look at the profile of your structure by having this height category. So now I will show you. So for V seat, okay, so here, okay, we now try to calculate all this. V dash equals to V seats. So we now calculate V seat, okay. Therefore V seat is equivalent to Vs times the MD times with MZ cat times with the M shielding, which is negligibles in our case, and MH. So now we know that Vs is 33.5, so MD is equivalent to 1, and then you have the MZ cat, which is difference at difference height, and then this is again 1.0, and here is 1.0. So the profile of the wind speed design, the wind speed is now for V seat, let's say we have at 40 meter is 33.5 times with MZ cat, so which is 0.85. So you can have 0.85, and V seat at 30 meter, so 30 meter is 0.8, Okay, 33.5 times 0.8, and you have V seat for 20 meter, the same, multiply by 0.75 if I'm not mistaken, and here is 10 meter, 33.5 times with 0.75. So now you calculate all this. Okay, you calculate all this, so here you will get 28.475 meter per second. So wait, I will need to have my calculators with me. Okay, alright, so now you calculate 33.5 times 0.8, you get 26.8. okay, and 33.5 times 0.75, you get 25.125. 33.5 times 0.75, you get 25.125. So all meter per second. So now you get your V seat, which is your profile for your structures. So profile for your structures, if you get here, okay, this is your building. Okay, this is your building. So 10 meter, 20 meter, 30 meters, and 40 meter. Alright, so you can have like a scales. At 10 meters it is like 25, 20 meter the same, 25, 30 meter it can be 26, and 40 meter it's like 28. So your structure could be like, continue the distributions. Okay, distributions. So those are the wind speed distributions to your structures. Okay, so now we have all the parameters that we required, so then we can calculate our V dash. Okay, so by inserting all the values that we have into these equations, so because of we have the V seats and etc., so our V dash, okay, our V dash is equivalent to V seat times the important factors. So where did you get the important factors from? So you have to refer to table 3.2. Okay, so now this is the table 3.2, which is important factor. So you can find what is the value here, the factors for the occupancy, and it is based on the category of structures. So in our case, we have to go by one. The first one is for agricultural facilities, okay, and minor storage facilities, which is not represent our category of building, which is located at EPO, and it is the office building totally enclosed. So all buildings and structure except those listed in 1, 3, and 4. This is for category 2. And third category, building and structures where the primary occupancy is which is more than 3,000 people. No. Essential building like hospitals, fire, police, communications, power stations. No. So basically our structure is category 2, which is the coefficient factor is given as 1. So now we know that our coefficient factor is 1 because it is category 2. So we can calculate V dash, which is equals to V seats times I, the important factor. So we now calculate V dash at 40 meter, V dash at 30 meter, V dash at 20, V dash at 10. So here, okay, V dash, you can say that V seat is equivalent to, as what we calculated this, we already now get V dash is 28.475 times 1. So basically they have the same value like what they have in V seat. So here is 25.1 times 1.0, and here is 25.125 times 1.0. So initially, what I'm trying to say, the design wind speed is more or less similar like their design basic wind speed, because the important factors here is 1. Otherwise, if the important factor is difference, then you might have a different value of V test. Okay, so this is 25.1 per second.